Across the dark skies of a planet cleared of artificial glare, it appears as a serene, luminous river, a spill of celestial milk arcing from horizon to horizon. This is the view from within, a cross-section of our own galactic home, the Milky Way. To an observer positioned deep inside its structure, its full form remains an act of scientific reconstruction, a map drawn from the careful measurement of stellar distances, the tracking of hydrogen gas clouds, and the patient cataloging of light across the entire electromagnetic spectrum. From this painstaking assembly of data emerges the portrait of a barred spiral galaxy, a vast, spinning disk of stars, gas, and dust measuring approximately 100,000 light-years from one edge to the other. Within this stellar metropolis, our own Sun is a nondescript resident, orbiting the galactic center from a quiet suburban location in a minor spur known as the Orion Arm, some 27,000 light-years from the core. The galaxy's total mass is estimated to be close to 1.5 trillion times that of our star, a number so large it resists intuitive grasp. Yet, for all its seeming immensity, for all its hundreds of billions of stars and the profound emptiness that separates them, the Milky Way is but a standard, even modest, example of its kind, a single, glowing island in an archipelago of unimaginable scale. Its true measure is found not in its own dimensions, but in its comparison to the true leviathans of the cosmos, the galaxies that occupy the gravitational thrones of the universe. To comprehend this comparison, one must first intimately understand the architecture of our own galactic island. The Milky Way is a system of profound complexity and dynamism, a structure defined by motion and transformation over deep time. Its most prominent features are the spiral arms, which are not solid, rotating structures like the spokes of a wheel, but rather persistent patterns of higher density, compression waves that sweep slowly through the galactic disk. As clouds of interstellar gas and dust encounter the leading edge of one of these density waves, they are compressed, triggering gravitational collapse and igniting furious bursts of star formation. It is here, in these stellar nurseries, that the galaxy's youngest, most massive, and most brilliant inhabitants are born, the hot, blue O and B-type stars that illuminate the arms and give them their characteristic cerulean hue. These colossal stars live fast and die spectacularly, seeding the surrounding medium with heavy elements forged in their nuclear furnaces, elements essential for the formation of rocky planets and, eventually, life. The disk itself is a flattened structure, further divided into a thin disk of younger, metal-rich stars like our Sun, and a thicker, more diffuse disk of older, metal-poorer stars. At the heart of it all lies the central bulge, a dense, spheroidal congregation of ancient, yellow and red stars, swarming in more chaotic orbits around the galactic nucleus. And at the very center, shrouded by impenetrable clouds of gas and dust, lurks Sagittarius A, a supermassive black hole with a mass of just over 4 million suns, a gravitational anchor point for the entire inner galaxy. Surrounding this entire visible structure, extending far beyond the luminous disk, is a vast, spherical halo of scattered old stars and ancient, tightly bound globular clusters. Yet, all this visible matter, the stars, the gas, the dust, accounts for only a fraction of the galaxy's total mass. The rest, the overwhelming majority, resides in an even larger, invisible halo of dark matter, a mysterious, non-luminous substance whose gravitational influence is the silent force that binds the galaxy together, preventing its rapidly spinning disk from flying apart. This is the complete anatomy of our home, a vibrant, star-forming spiral, governed by an invisible scaffold of dark matter, a place of constant birth, death, and recycling. Scaling outward, the Milky Way is not an isolated entity. It is the second largest member of a small, gravitationally bound collection of galaxies known as the Local Group. This cosmic neighborhood, spanning roughly 10 million light-years, is dominated by two major spirals, our own galaxy and the Andromeda Galaxy, designated M31. Andromeda lies 2.5 million light-years away, and through a telescope, it appears as a faint, elongated smudge of light, yet it is the most distant object visible to the unaided human eye. It is our celestial sibling, and in many ways, our superior. M31 is significantly larger and more massive than the Milky Way, with a diameter of perhaps 220,000 light-years and containing as many as 1 trillion stars. It is a more dominant gravitational presence, its pull shaping the orbits of the smaller galaxies around it. The third largest member, the Triangulum Galaxy, M33, is a smaller spiral, and the rest of the local group's population consists of over 50 dwarf galaxies, irregular and spheroidal collections of stars that orbit the two giants like moths around a flame. The Large and Small Magellanic Clouds, visible as detached fragments of the Milky Way from the southern hemisphere, are two such satellites of our own galaxy. This entire assembly, the local group, exists in a state of delicate gravitational conversation. Spectral analysis of the light from Andromeda reveals a blue shift, indicating that it is not moving away from us, as most galaxies are, but is instead hurtling toward the Milky Way at a speed of over 100 kilometers per second. Models of this trajectory predict a titanic collision and subsequent merger between the two galaxies, an event set to begin in approximately 4.5 billion years. This is not an act of destruction, but of creation. Over hundreds of millions of years, the two spirals will pass through one another, their individual stars missing each other in the vastness of space, but their vast clouds of gas and dust will collide, triggering a galaxy-spanning starburst of unimaginable intensity. Eventually, their gravitational fields will tame the chaos, and they will settle into a single, much larger, and more quiescent entity, a giant elliptical galaxy, a new creation bearing little resemblance to its spiral progenitors. This process of collision and merger is a fundamental mechanism of galactic evolution, a common narrative written across the cosmos. To find the true giants, however, one must travel far beyond the quiet celestial suburbs of the local group. The journey leads to the great metropolises of the universe, the massive galaxy clusters. These are the largest gravitationally bound structures known, dense congregations of hundreds or even thousands of galaxies, all orbiting a common center of mass within a volume of space millions of light-years across. One such nearby example is the Virgo cluster, whose center lies over 50 million light-years away. Unlike the local group, which is dominated by spirals, the Virgo cluster's core is populated primarily by enormous, featureless elliptical and lenticular galaxies. Here, the galactic environment is profoundly different. The space between the galaxies is not a near-perfect vacuum but is filled with a tenuous, searingly hot plasma known as the intracluster medium, a gas heated to tens of millions of degrees and detectable only by its X-ray glow. Galaxies within this dense environment move at tremendous speeds, often exceeding 1,000 kilometers per second, making close encounters and collisions far more frequent and violent than in sparser regions of space. A spiral galaxy unfortunate enough to fall into the core of such a cluster is subjected to immense environmental stress. The pressure of the hot intracluster medium can strip the galaxy of its cool gas in a process called ram pressure stripping, effectively removing the raw fuel for star formation and prematurely quenching its evolutionary fire. The constant gravitational tides from its thousands of neighbors can disrupt its delicate spiral structure, pulling and distorting it over eons. In these cosmic cities, the rules are different, and survival favors the massive and the compact. And at the very heart of the most massive clusters, at the bottom of the deepest gravitational wells in the universe, reside the kings of the galactic kingdom. These are the brightest cluster galaxies, or BCGs, a class of object to which nothing in our local group, not even the future merged Milky Way and Andromeda, can compare. To gaze upon one of these titans is to witness a scale that fundamentally challenges our terrestrial and even our galactic sense of proportion. Consider the galaxy IC 1101, the central dominant galaxy of the cluster Abell 2029, located approximately 1 billion light-years from Earth. Where the Milky Way's stellar disk spans 100,000 light-years, the diffuse halo of stars that constitutes IC 1101 extends for a staggering distance of at least 4 million, and perhaps as much as 6 million, light-years. If it were placed where the Milky Way is, its outer edge would stretch far beyond the Andromeda galaxy. It is a structure so vast that a beam of light, the fastest thing in the universe, would require millions of years to traverse its diameter. Its stellar population is estimated to be in the vicinity of 100 trillion stars, 1,000 times that of our own galaxy. This is not simply a larger version of a galaxy like the Milky Way, it is a different phenomenon altogether. The Milky Way is an island, IC 1101 is a continent. Its gravitational domain is not merely its own structure but the entire Abell 2029 cluster, a system containing thousands of other galaxies, all of which are ultimately subject to its immense pull. The light from IC 1101 is ancient and uniform, a pale, golden-white glow that lacks the brilliant blue highlights of active star formation. It is a vision of cosmic antiquity, a relic from a different era of the universe, and its very existence is a testament to a long and violent history. The visual form of a BCG like IC 1101 is as alien as its scale. It possesses none of the elegant, ordered structure of a spiral galaxy. There are no graceful, sweeping arms, no intricate dust lanes, no bright, glowing nebulae. Instead, it is a colossal, amorphous spheroid of light, a diffuse cloud of stars that grows steadily fainter from its bright core to its impossibly distant, tenuous edge. It is the archetype of a CD-type galaxy, a supergiant elliptical with an extensive, low-surface brightness halo. The stars that comprise this immense system are, on average, far older than those in the Milky Way's disk. They are predominantly population II stars, ancient objects that formed early in the universe's history, and they are characterized by their lower metallicity, a comparative lack of elements heavier than hydrogen and helium. Their collective light gives the galaxy its characteristic yellowish-red hue, the color of cosmic twilight. This is a galaxy defined by quiescence. The vast spaces between its trillions of stars are devoid of the cold, dense molecular clouds necessary to form new generations of stars. It is, in the parlance of astronomers, a red and dead galaxy. Its era of vibrant, youthful star birth is a distant memory, lost in the deep past billions of years ago. Its present state is one of monumental stability, a placid giant resting at the center of its cosmic domain. This serene appearance, however, belies the extraordinarily violent processes that forged it. A galaxy like IC 1101 was not born this way, it was assembled, piece by piece, over the entire age of the universe. The history of a brightest cluster galaxy is a story of relentless galactic cannibalism. At the center of a forming galaxy cluster, the densest point in a vast region of space, a large galaxy begins to form. As the cluster evolves, the laws of celestial mechanics dictate a grim fate for many of its members. A process known as dynamical friction acts as a cosmic brake on the most massive galaxies orbiting near the center. As a galaxy moves through the cluster, its immense gravity creates a wake of stars, gas, and dark matter behind it. The gravitational pull of this wake, in turn, tugs backward on the galaxy, causing it to lose orbital energy and spiral slowly but inexorably toward the cluster's gravitational core. At that core lies the central galaxy, which acts as a cosmic predator. Over billions of years, it consumes its neighbors one by one. Dozens, and then hundreds, of smaller galaxies, spirals, ellipticals, and irregulars, are tidally shredded and absorbed. Their stars are stripped away and added to the ever-growing, diffuse halo of the central giant. Their gas is incorporated into the intracluster medium, and their central black holes sink toward the core of the BCG, eventually merging with its own supermassive black hole. This process, known as hierarchical merging, is the engine of a BCG's growth. The smooth, featureless appearance of IC 1101 is the result of this long history of violent mixing. The distinct structures of the consumed galaxies have been erased, their stars scattered and randomized into a single, colossal, and relatively homogeneous sphere. The giant is, in essence, a ghost built from the remains of countless other galaxies, its immense size a direct consequence of its position at the nexus of cosmic traffic. This history of accretion also explains the profound difference in the lifeblood of galaxies, their gas content and star-forming activity. In the Milky Way, the interstellar medium is a dynamic, multi-phase system. Vast clouds of cold, molecular hydrogen, the raw fuel for stellar birth, are abundant in the spiral arms. This gas cools, fragments, and collapses under its own gravity to form protostars. The energy injected back into the medium by young stars and supernovae helps to regulate this process, creating a self-sustaining cycle of creation that has persisted for billions of years. In the environment of a BCG like IC 1101, this cycle has been completely shut down. The dominant gaseous component is the intracluster medium, a diffuse plasma heated to temperatures of 10 to 100 million Kelvin. This gas, which represents more baryonic mass than all the stars in all the cluster's galaxies combined, is simply too hot and too low density to cool and form stars. Any cool gas that might have been present in the galaxies consumed by the BCG was either shock-heated upon entering the cluster or stripped away long before the final merger. The result is a state of cosmic starvation. But there is another, more active mechanism at play. At the heart of IC 1101 lies one of the most massive supermassive black holes ever discovered, with estimates of its mass reaching into the tens of billions of solar masses. While this behemoth is not accreting matter at the furious rate of a quasar, it is not entirely dormant. A slow trickle of hot gas from the intracluster medium cools and flows toward it, feeding it just enough to power immense, relativistic jets of plasma that blast outward into the surrounding medium. This process, known as AGN feedback, acts like a thermostat, injecting vast amounts of energy back into the cluster's core, preventing the hot gas from ever cooling sufficiently to rain back down onto the galaxy and trigger a new era of star formation. The galaxy is effectively sterilized by the heat of its own environment and the activity of its own central monster. The most fundamental difference, the invisible architecture that underpins all others, lies in the realm of dark matter. The Milky Way's dark matter halo is a colossal structure, perhaps 2 million light-years in diameter, and its gravitational field dictates the rotation speed of our galaxy's disk and the orbits of its satellite dwarf galaxies. It is the local sovereign of the local group. The dark matter halo of a galaxy like IC 1101 operates on an entirely different plane of existence. It is not merely the halo of a single galaxy, it is the halo of the entire Able 2029 cluster. This single, monolithic structure of dark matter extends for many millions of light-years and contains a mass equivalent to over 100 trillion suns. The visible galaxy of IC 1101, despite its own staggering size, is merely the luminous tip of the iceberg, a concentration of baryonic matter settled at the very bottom of this unimaginably deep and wide gravitational well. This dark matter empire is the true source of the BCG's dominance. Its gravity is what binds the thousands of cluster galaxies into a single system, what funnels them toward the center for consumption, and what holds the superheated intracluster medium in place. The sheer mass of this halo warps the fabric of spacetime so profoundly that it acts as a powerful gravitational lens, bending and magnifying the light from far more distant galaxies that lie behind the cluster, creating distorted arcs and multiple images of these background objects. By studying these lensed images, astronomers can map the distribution of mass within the cluster and confirm the overwhelming dominance of the dark matter component. The Milky Way's halo defines a galaxy, IC 1101's halo defines a cosmic superpower, a gravitational entity that shapes a significant volume of the universe around it. In the grand cosmic ecology, the Milky Way and IC 1101 represent two profoundly different states of being, shaped by two different environments and two different histories. Our galaxy is a field spiral, living in a low-density region of the universe where it has been allowed to evolve in relative peace, maintaining its delicate structure and its capacity for ongoing star formation. It is a system in its cosmic prime, a place of vibrant activity and creative potential. Its destiny, a merger with Andromeda, will eventually transform it into a larger elliptical, but even this future creation will pale in comparison to the established giants. IC 1101, by contrast, represents a state of galactic maturity, or perhaps senescence. It is a product of its extreme environment, its form and fate dictated by its privileged position at the nexus of a massive cluster. Its growth has been driven by destruction, its current tranquility a result of having consumed everything within its reach and its furnace having been extinguished by the feedback from its own central engine. It is an ancient capital, a sprawling, static empire built upon the ruins of its neighbors. This comparison reveals that a galaxy is not just a collection of stars, but a product of its environment and its place within the cosmic web, the vast, filamentary structure of matter that spans the universe. Galaxies flow along these filaments like water in a river system, trickling into groups and eventually pouring into the great reservoirs of the clusters. The Milky Way is a vessel on one of these cosmic rivers, while IC 1101 is the vast, still lake at the river's end. In studying these two extremes, our familiar home and the distant, incomprehensible giants, we trace the epic life cycle of structure in the universe, a story of quiet growth, violent collision, and eventual, majestic quiescence, written in light and gravity across billions of years.